This is the second video for week 9. In this slide, we're going to talk about what it means for it to be cohesive. We already know that a cluster refers to a dense subgraph. And one way of thinking about a cluster is that most of the vertices are joined to each other. So if the edges represent similarity, then we can say that the vertices are jointly similar. So vertices that are jointly similar within a given cluster is a measure of cohesiveness. Now, what types of clusters are we seeking? There are two types that we can talk about. The clusters can be exclusive, or they can be intersecting or overlapping. In the case that they are exclusive, what we actually have is a partition of the vertex set, and so the process is called a cluster partition. If the clusters are allowed to overlap, then we seek to obtain a cluster cover. Now, in the preceding slide, we talked about two different types of clustering, whether the clusters overlap or not. But how do we find these clusters? Well, part of it will depend on our objective. What are we hoping to achieve by clustering the graph? Or what is more important to us in the end result? If it's more important to us that we have a high level of similarity or denseness within our clusters, and that is, we want to have cohesiveness determining the clusters, then that is our objective. On the other hand, if we know how many clusters we want, and so it's not as important to us as whether or not the clusters are cohesive, it's more important to us as how many clusters we want, then that is the second type of approach. So it depends upon your objective, whether you want cohesiveness or the number of clusters to determine your algorithm. So back to the question, how do we determine clusters? Let's suppose that cohesiveness is more important to us. So we want dense clusters, even if we have to have quite a few of them, or quite, on the other hand, maybe not so many. If the denseness of the cluster or the cohesiveness is what's making our decision, then our algorithm might be one in which we search for complete subgraphs. Complete subgraphs are sometimes called cliques. So how do we find cliques in a graph? Well, one approach is we can find actually an independent set, and then find the complement of, first find the complement of the graph, and then find the maximum independent set. And this will give us a clique in the original graph. We can sometimes use the concept of the graph complement to help us find a clique. For example, if we know that the largest independent set is of order 2 in a given graph, this will tell us that in the complement, the largest clique is also 2. And in fact, we can generalize this, that if the clique number of the graph is k, then the independence number of the complement is also k. Now recall type 2. Type 2 is where we decide how many clusters that we want to have. And so we say we want k or no more than k clusters. How do we decide what k is? One method that we can look at is using the domination number of the graph. You've probably heard of different algorithms that are of this type, like the k-means algorithm. So we associate with a given vertex a cluster, and we call that vertex the head or the center of the cluster, and therefore we have k heads. So if we have a domination number, we can set that as our value for k. And we will associate with each element or each vertex in the dominating set a cluster. For example, we looked at the RNA trees, and we saw that this given tree has a domination number of 3. So we can choose each vertex in the dominating set and take it together with its neighbors as a cluster. That should give us 3 clusters. So we obtain the 3 clusters as indicated below. We have the red cluster, the blue cluster, and the black cluster. Notice that this is a cluster cover because our clusters overlap. We could alter the definition and at each step remove the vertices that we have selected and then choose the next domination number from what is left over. If we want a cluster partition rather than a cluster cover, we most likely would want an independent dominating set. If we have, as below, an independent dominating set, then when we choose a vertex in the dominating set to be the head of our cluster, then when we remove it together with all of its neighbors, we will not be removing another dominating vertex if the dominating set is independent. So we can decide whether we want to use an independent dominating set because we want to have a cluster partition, or if that's not necessary, then we wouldn't necessarily want to take an independent dominating set. But let's see what happens in this case. There are variations on the algorithm. So we could say each time we choose a vertex in the dominating set, we will take it together with its neighbors. And then it would depend upon which vertex in the dominating set we happen to choose first. So on top, it looks like we chose the vertex on the left first. That left one vertex in the dominating set of degree 4, which we took. On the bottom left, it looks like we chose the vertex of degree 5 first. And then on the bottom right, we did not remove the neighbors of the chosen vertex. We just simply took the next vertex in its neighbors, which gave us the overlapping. Okay, so one more example. Using Peterson's graph in this independent dominating set, we can choose the vertex 1 and take its neighbors 2, 5, and 9, and that's our first cluster. So we're going to have a cluster partition since we're taking neighbors with us. So that leaves, we can take the vertex 6 next and take it and its 2 neighbors 7 and 10. That just leaves the vertex 4 with its 2 neighbors 8 and 3. So the 3 resulting clusters that correspond to the domination number 3 are given below. Now, recall that I believe we found the clustering coefficient of Peterson's graph in her earlier exercise. And if you look at the neighbors of each vertex has degree 3. And let's say we look at vertex labeled 10. Its neighbors are 6, 9, and 3. So if my memory is correct, every vertex induces a neighborhood that's independent. So actually, Peterson's graph has clustering coefficient 0. So how do we obtain clusters from a graph that has clustering coefficient 0? Well, we're making most out of a bad situation. What we can do when we have these clusters is we can find subgraphs that are relatively dense compared to the graph itself. In addition, these individual clusters have a short average path length because they are all adjacent to the head. So the average length is less than 2. Or it's 2 or less than 2, depending on if we have an induced edge. So the individual clusters, compared to the graph as a whole, have desirable effects, although this graph as a whole is not highly clustered.